Welcome to Gradient Daily. Today, we're examining a new paper titled Argus. The objective is to extract geometrically consistent, metric 3D point clouds from 360-degree panoramic images. Automated real estate mapping, mixed reality applications, and autonomous indoor robotics rely on precise spatial measurements. Visual approximations fail when a drone needs to navigate safely through a complex, multi-room environment. Here's the paradox. Feed-forward neural networks are highly capable of extracting 3D geometry from narrow field-of-view images. Yet, when tasked with holistic panoramic reconstruction, their performance collapses due to a severe lack of training data. Think of standard RGBD datasets like looking through a keyhole. Your view is a narrow 2D cone intersecting a small patch of a wall. A 360-degree panoramic capture observes the entire geometry of a room simultaneously. Without access to large-scale panoramic training data, models have no way to learn the global context required to understand room-scale geometry. Achieving accurate panoramic 3D reconstruction requires datasets built from the ground up to prioritize massive scale and precise metric annotations over simple visual variety. To solve this, the researchers introduce RealC3D, a baseline hybrid dataset designed specifically to bridge the panoramic data gap. Looking at this chart, RealC3D contains 10,000 indoor scenes and 299,000 panoramic viewpoints. 9,000 scenes are synthetic, providing noise-free ground truth geometry to learn absolute scale. The remaining 1,000 real scenes force the network to adapt to sensor noise and complex lighting. Blending these two distributions provides the necessary foundation to train a metric-aware feed-forward network. The core geometric challenge Argus tackles is sparse, unordered capture. This occurs when a user takes random 360-degree photos throughout a room, and the network must fuse them into a single metric world frame. This introduces what we'll call the anchor problem, the mathematical danger of arbitrarily picking one of those random captures as the absolute origin point for the coordinate system. Imagine a surveyor trying to map a coastline at night. If you use a small, heavily bobbing ship as your reference anchor, the unstable movement guarantees your entire map will be misaligned. This same principle applies to camera geometry. If a network chooses a poorly aligned coordinate anchor in a panoramic capture, it causes global pose drift. Even a minor alignment error at the first node compounds across a large indoor scene, ultimately ruining the metric reconstruction. To solve this, Argus introduces its first major architectural innovation, the Learned Covisibility module. Covisibility is the mathematical evaluation of how much underlying 3D geometry is shared between different panoramic viewpoints. Rather than guessing, the module dynamically evaluates every available viewpoint in the unordered capture to measure these shared spatial volumes. The network then calculates the geometrically optimal reference view to act as the permanent anchor, our surveyor's lighthouse, securing the entire metric world frame. By replacing heuristic anchor selection with calculated learned covisibility, Argus mathematically eliminates the root cause of global pose drift before reconstruction even begins. Once the frame is anchored, the architecture splits into multitask learning branches for depth estimation, camera pose estimation, and point cloud reconstruction. This flowchart illustrates the concept of bidirectional mapping, translating 2D panoramic pixels into a 3D world space, and then projecting that 3D world space back into 2D pixel space. Think of the cycle translation constraint used in linguistics. If you translate a technical manual from English to Japanese and back to English, the final result exposes any errors in the first translation. Applying this to Argus, if the depth prediction doesn't match the reverse pose projection, the network generates an immediate error signal. Argus handles this massive pixel-to-world mapping by decomposing it into smaller, interpretable substeps. The researchers introduce cross-coordinate joint constraints, forcing the depth estimation and camera pose branches to mathematically cross-check each other's work. During training on the RealC3D dataset, per-step supervision is applied to these exact constraints. This forces the model to ground its predictions in hard geometric reality, rather than just memorizing latent feature correlations in the synthetic data. Decomposing the mapping into constrained substeps creates a feedback loop where multitask constraints actively elevate the accuracy of single-task predictions, like baseline depth. This chart outlines RealC3D benchmark results. Argus achieves state-of-the-art performance across pose estimation, depth estimation, and point cloud reconstruction. The results show cross-coordinate constraints, improved baseline depth estimation, even compared to exclusively depth-trained models. Prior feed-forward models typically fail in sparse panoramic settings because they lack dynamic reference anchoring to stabilize their predictions. Argus's benchmark performance suggests enforcing strict geometric consistency through architecture is a more effective design choice than simply increasing a model's parameter count. Argus addresses the pose drift problem while providing the research community with a robust, large-scale dataset. However, the model's performance in highly complex, cluttered real-world rooms full of reflective surfaces remains a point for further study, given the massive synthetic split. Second, the architecture assumes static indoor scenes. It is currently unclear how the co-visibility module handles moving subjects or changing environments during capture. Future work will likely test this architecture in dynamic outdoor environments, such as autonomous driving systems utilizing panoramic cameras. A second research vector involves integrating Argus's precise metric anchoring with Gaussian splatting to enable photorealistic novel view synthesis of indoor spaces. While Argus is currently evaluated on static indoors, its mathematical foundation establishes a framework for universal metric scene understanding. To summarize, first, RealC3D addresses the panoramic data bottleneck by providing 10,000 metric scenes for scale and ground truth. Second, Argus eliminates global pose drift by using a learned co-visibility module to dynamically anchor coordinate frames. And third, decomposed bidirectional mapping utilizes cross-coordinate constraints to enforce geometric reality across all multitask predictions. That's it for today's breakdown. If you found this research analysis helpful, like, subscribe, hit the notification bell, and join us tomorrow on Gradient Daily for our next AI paper review.